Nuclear equations represent nuclear change in much the same way as chemical equations represent chemical change. A nuclear equation can be used to represent the process of radioactive decay. In radioactive decay, a nuclide breaks down, producing a new nuclide, smaller particles, and/or energy. The concept of mass balance required when writing chemical equations is also essential for nuclear equations. When writing a balanced equation, remember that the total mass on each side of the reaction arrow must be identical, and the sum of the atomic numbers on each side of the reaction arrow must be identical. Consider the decay of one isotope of uranium, uranium-238, into thorium and an alpha particle. Because an alpha particle is lost in this process, this decay is called alpha decay. Look at the balanced equation for this nuclear reaction. The sum of the mass numbers on the right, 234 plus 4, is equal to the mass number on the left. 234 plus 4 gives you 238. The sum of the atomic numbers on the right, 90 and 2, also shown down here, is equal to the atomic number on the left. And so you can see the total masses on each side of the reaction arrow are equal. 238 is equal to 234 plus 4. And the sum of the atomic numbers on each side of the reaction arrow is also identical. 92 is equal to 90 plus 2. Beta decay is illustrated by the decay of one of the less abundant nitrogen isotopes, nitrogen-16. Upon decomposition, nitrogen-16 produces oxygen-16 and a beta particle. Conceptually, a neutron is equal to a proton plus an electron. In beta decay, one neutron in nitrogen-16 is converted to a proton, and the electron, the beta particle, is released. The reaction is represented as shown here. And you can see that this is our beta particle right here. Our beta particle, and that in order to balance the reaction, when the nitrogen-16 decays to give you the beta particle, the sum of the mass numbers must be equal on both sides of the reaction. You can see that we have 16, nitrogen-16, that's the mass number of the nitrogen, and I'm forming oxygen-16 and the beta particle, and the beta particle has no mass number, so 16 plus 0 is equal to 16. And you can see that the sum of the atomic numbers on both sides of the reaction arrow are equal. 7 is equal to 8 plus -1 from my beta particle. The decay of carbon-11 to a stable isotope, boron-11, is one example of positron emission shown here. The reason there are two equations here is that they're both showing different ways to represent the positron. So this is a positron, and this is the same thing, just written a different way. This is another way of representing a positron. A positron has the same mass as an electron or beta particle, but opposite charge, so the charge is +1. In contrast to beta emission, the product nuclide has the same mass number as the parent nuclide, but the atomic number has decreased by 1 unit. The atomic number on the left, 6, is counterbalanced by 5 plus 1 on the right. Therefore, the equation is correctly balanced. If gamma radiation were the only product of nuclear decay, there would be no measurable change in the mass or identity of radioactive nuclei. This is so because the gamma emitter has simply gone to a lower energy state. An example of an isotope that decays in this way is technetium-99m. The lowercase m represents a metastable isotope, meaning that it is unstable and increases its stability through gamma decay without change in the mass or charge of the isotope. The decay for technetium-99m, or technetium-99 metastable, is shown here. So again, this lowercase m just represents that it's a metastable isotope, which means it's energetically unstable, and to increase its stability, it emits gamma rays. And gamma rays are simply represented by the Greek letter gamma. It's possible to use a nuclear equation to predict one of the products of a nuclear reaction if the others are known. And so this is one of the main take-home messages for Chapter 9, is that you should be able to predict the products of nuclear decay. And in order to do that, to predict the product, simply remember that the mass number and the atomic number are conserved. So you can see here we have the decay of uranium-239, and we're emitting a beta particle. Remember, this is a beta particle, or one of the ways of representing a beta particle. And the mass number for my uranium is 239. The beta particle has a mass of 0, and therefore X must have a mass number of 239. So we'll write that down here. We'll put 239. And then as far as the atomic number is concerned, well, my uranium has an atomic number of 92, but the atomic number of X has to be greater than 92 because that number minus 1 is going to be equal to 92. So you have to ask yourself, what plus negative 1 gives me 92? Well, hopefully you know that 93 subtract 1 gives you 92. So the answer for the atomic number is 93. And then if you go over to the periodic table and you look up what's element 93, and you go down, you look for element 93, and you see it's represented by the symbol Np, which is neptunium, and therefore you would put that in for your atomic symbol. And this is the answer. It's neptunium-239 is what X is.